right, welcome to Chapter 4, where we are going to take what we learned in Chapter 3 about all of our techniques with derivatives and apply some of that, mainly to some graphing things as well as some optimization problems that we will see later on. So, Chapter 3 was all about techniques on how to find a derivative. Chapter 4 is now going to apply those techniques to application problems of derivatives, many of which concern properties of functions and their graphs. The one we will look at early is a set of analytical curve sketching methods that produce accurate graphs of functions. Now, this is one of the fundamental tasks of calculus that we will begin now. Many applications ask the question about maxes and mins of functions on a given interval or a domain. Where is the function the largest and where is it the smallest? This becomes significant when a function represents a practical quantity, such as profits on a company, the surface area of a container, or the speed of a space vehicle. So, like if you want to maximize your profits in a company, you can create a model of your profits and maximize that using calculus. If you're wanting to minimize the surface area of a container to ship something as you're manufacturing, you can use calculus to do that, okay? So, talking about absolute maxes and mins is our first task. That's going to be looking at the function. So we're going to say let f, let me get my pens going here. Let f be defined on a set D containing C. So D representing the domain, C representing some number. If the function value at C is greater than or equal to any f of x for every x in D, then that f of C, remember that's a y value, is what we will refer to as an absolute maximum. Should make sense that if it's larger than everything else, it should be a maximum. And that is going to be a maximum value of f on D, on that domain. Now, if we do the reverse of that, if f of C is less than or equal to f of x for every x in our domain D, then that y value, again, that f of C, is what we would refer to as an absolute minimum value of f on D. Now, when we talk both of them together, that's what we refer to as an an absolute, undo that, an absolute extreme value. So, talking about both of them together collectively, we can talk about absolute extreme value. Sometimes we refer to it as absolute extremum, etc. Okay? Now, the existence and location of absolute extreme values depends on both the function and the interval of interest. So let's look at some examples. I'm going to look at kind of the graph y equals 4 minus x squared, which is a parabola that is shifted up by 4, reflected over the x-axis. And so, it looks something like this, 1, 2, 3, 4. And if I just draw the graph collectively, this is at -2, that's at +2. Here, in a sense, when we talk about absolute extremum, then here I do have an absolute max because that is the highest point. So we would have an absolute max of 4 at x equaling 0. The maximum is the y value, but we also refer to it as where it is at x equaling 0. But notice here that I have these going down forever and forever and forever. There is no absolute min. So this is a situation where we have an absolute max, but no absolute min. So you may want to write that too. No absolute min, so that you have it on there. Now, if I restrict that graph to a domain that is from 0 to 2, okay? And in these cases with the solid dots, I'm including 0 and 2. Notice I would end up then having an absolute max of 4 at x equaling 0. And I have a bottom out point here. The y value of that is at 0 when x equals 2. So I do have an absolute min of 0 at x equaling 2 in this situation. Okay? But I could also change this up again and restrict to where I include one of those, but exclude the other. So maybe we exclude up here at 4, but I do include right here. Notice that this graph will come close and close and close up here to to y equaling 4, but it will never reach that. So if I don't include a point here, there is no absolute max or min at that non-included point. So there is no absolute max here, but I do have an absolute min here because I'm including that. Absolute min of 0 again at x equaling 2. And then the final kind of situation using this same example would be that I include this but not include this value down here. Again, we're treating this as the graph y equaling 4 minus x squared. So here we're at 0, there we're at 2. Here we do have an absolute max of 4. That's the y value at x equaling 0. There's my x equaling 0. But here, there is no absolute min. Okay? So, here's all kinds of different situations. So when you're asked to graph something like that, then you can kind of mold it to what you need in order to create the conditions that you're given. Okay? Now, but a closed interval does not yield absolute extrema all the time. So let's look at this. If I look at a graph, say I'm including here the origin, I have a linear graph that I'm not including that point, but I drop that point down here on the axes. So I do have a closed interval. Say that we're from 0 to 1 or something like that. Here, this is a closed interval from 0 to 1, but I do have absolute mins. These are going to be my absolute mins because they are the lowest points that I have, and that minimum is 0. But here we have at x equaling 0 and x equaling 1. But I do not have an absolute, no absolute max. There is not an absolute maximum there. Whoops, sorry. Okay. Now, if I look at another graph that has a closed interval, say we go from A to B, and I do something like this, where I'm including here, but then I jump and I create that graph there. Actually, let me edit that just slightly to what I want. And on these screencasts, feel free to pause anytime if I'm going too fast for you to write. Then, if I have this, again, I've got a closed interval from A to B. I don't have a continuous function, but I do have a closed interval because all points are accounted for. Here, I do not have an absolute max. There is not a point up here. So again, here, there's no absolute max, but I do have an absolute min that is here at A. So we have an absolute min of, well, whatever this, we'll call it f of A, because we don't know what it is, of f of A at x equaling A. So those we have some extrema, but not both, and we are on closed intervals. So the point of this is talking about this extreme value theorem that we have coming up next. How can we guarantee that we have absolute max and an absolute min on a closed interval? Well, the reason is we have to guarantee continuity. So there are two conditions that hold true, that you are guaranteed to have an absolute max and an absolute min. One is that a function is continuous. And two is that it has to be on some closed interval. It cannot be on an open interval, assuming that we have, one of those open circles or something like that. Has to be a closed interval, and then we are guaranteed an absolute max and an absolute min value. Okay? So, if we are guaranteed that, can we, for this function that we see here in A and B on these graphs, determine, do I have absolute max and min? Well, in graph A, notice I do have a nice continuous function. Check. We have that. It is on a closed interval. Check. Therefore, I will have an absolute max and an absolute min by this theorem. So on part A, continuous on AB, those are the two things that I have to check. So we will have an absolute max and an absolute min. Now, where are those? Well, notice here we don't have any y values, but we can say what x values that we have. The highest point that I have is here at A. The lowest point along my y-axis is this guy that's right here at C. So we have an absolute max at x equaling A and an absolute min at x equaling C. So here's my min and here's my max. Okay? Now, for graph B, do both of these conditions hold true? Do I have a continuous function from A to B? Absolutely not. Here, this means that the limit from the left, the limit from the right is not equal. Therefore, we are not continuous. Therefore, I cannot use the extreme value theorem, and there's no guarantee that I will have an absolute max or an absolute min in this situation. So we have to observe everything. It is also not on a closed interval. So we are not continuous, and we have an open interval, AB. So we are not guaranteed by the extreme value theorem to have both. So if we look at our picture, though, the bottom out point would be possibly this guy right here, but it is an open circle. So here, this means there is no minimum. But if I look here on this part, they have an included point here, and it is the highest. So therefore, I would have an absolute max here at x equaling C. So absolute max at x equaling C, no absolute min in this case. So again, the guarantee to have both means that I'm continuous on a closed interval. I am guaranteed to have both an absolute max and an absolute min, possibly more of the same. I mean, it could have like two absolute maxes or two absolute mins or more if they are the same. But if those two things do not hold true, you cannot guarantee an absolute max and an absolute min like what we have here in part B. Okay, let's continue that idea. Dealing with local max and local min. So an absolute max means that's the highest you can be. Absolute min is the very lowest you can be. But sometimes we have graphs that bounce in between, and there are some local maximum or minimum. Basically, is there a bottom out portion on a certain interval, on a very small interval, to where we have a minimum or a maximum, and that's what we're going to talk about. So suppose that C is an interior point on some interval I on which our function f is defined. If, this will look similar to the last one, f of C is greater than or equal to f of x for all x in I, then that f of C is a local maximum value of f. Notice we went from D being the domain to I being a smaller interval. Now, if f of C is less than or equal to f of x for all x in a smaller interval I, then that f of C is a local minimum value of f. So, I've given you an illustration from the book as to what some absolute max and mins are. Notice that the highest point that I have, it is a nice continuous function on a closed interval, so I would be guaranteed absolute max and mins by the extreme value theorem. The highest point that I see is this one right here. Notice it does say that it is an absolute maximum, but we also can constitute that as a local maximum as well because it is on a smaller interval, the highest point on a smaller interval as well. So there would be a local max. Another local max would be this guy over here. So if I look at this interval around Q, then I have a maximum in that area. And then I can also see within that interval, not including A and B, but within that interval, there are two kind of valleys. We can call them peaks and valleys if you want. So the valleys that we have here at P, N, and R are what we refer to as local minimum. Okay? All right. Oh, and we do include an absolute minimum over here. This is the smallest point here. So here, this is a good picture that has all different kinds. Absolute max, absolute min, local max, and a local min. Now, can we identify the location of any absolute or local extrema in this case right here? Now, we're going to assume that these are in the same y value. here. And notice that's kind of the highest point. We have a nice continuous function, closed interval, so I'm guaranteed absolute max and mins. So, excuse me, the absolute max here is when x equals q and s. So at q and s, we have absolute max. Now, remind yourself that those are also constituted as local maxes as well at q and s. So don't forget that. So these are our peaks. Our valleys are going to be the lowest points. Now, where is the most bottom out point that we have? And it's going to be this guy right here. So I'm going to constitute that my absolute min is at x equaling p. I can also constitute that as a local min. And notice on a smaller interval, I have a bottom out point right here at r as well. So I can constitute that we have a local min not only at p, which is also the absolute, but also at r as well. Okay, so where do we go from here? Well, how can we relate this to derivatives? So if we look at each one of these, notice this nice smooth curve. What would happen when we talk derivative? We're talking the slope of a tangent line. Here we would have a slope of a tangent line. Notice we do see those over here as well. Notice that we have the slope of our tangent lines being equal to 0. That's that highest out point. We've seen that in some of our projectile motion problems as well. But also we need to remind ourselves about this guy right here. We kind of talked about it, but not very much. And this is a pointy point, is what I refer to it as, a sharp turnaround point where the derivative from the left is not going to equal the derivative from the right. We also have that over here. Sometimes they call these cusps, to where we have a sharp turnaround point right here, and we have a sharp turnaround point right here. Those don't have derivatives equal to 0. Those have derivatives that are not existent. So, we look at local max and mins above. What is true about the derivative at these points? Either the derivative has to equal 0, where I have a horizontal tangent in all these cases right here, but in these two cases, right here and right here, I have a derivative that does not exist. So this is the pointy point, is the way I refer to it, and this is our horizontal tangent. And those are important because that's where your local extrema is going to occur. Now, most of the time we look at the case where it's equal to 0 more so than the do not exist, but we have to make sure that we have both. So, for our local extrema value theorem, if f has a local maximum or minimum value at some c, then f prime of c exists and it's equal to 0 in one of the cases. Okay, that's where we have those nice smooth curves and those horizontal tangents right here, right here, right here, and these two over here. Actually, these three over here. Okay, but to remind ourselves of two graphs in which our derivative doesn't exist. So we already talked about one. That is if I end up having kind of a cusp or a pointy point. Here, we would have an absolute max or a local max, but f prime, call this c, of c does not exist, b and e. And another situation would be if I end up having kind of an open circle here, but I also have this piece here. Actually, let me not put arrows. Let's put points here. Here I have some local minimums, okay? But I do not have a derivative that exists right here, okay? With that being not continuous, that derivative is not going to exist. Therefore, we can have some minimums on our functions, but here there would be no local max at this, okay? All right, very good. So, hence we have the following definition for both cases. And this is where we get our idea of critical points. Critical points are important because they're going to help us find these max and mins. So we're going to say that an interior point C of a domain of f at which f prime of c equals 0 or f prime of c fails to exist is called, maybe I should say a critical point of f. Okay. So we have a critical point of f at where our derivative equals 0 or where our derivative does not exist. Now, here's the thing to note. Note that the converse of this is not necessarily true, because it is possible that f prime of c at a point without a local max or min occurring there at where f prime of c is equal to 0 or f prime of c does not exist. Now, if it is also possible that f prime of c does not exist with no local extreme values occurring at c, therefore, critical points are what we refer to as candidates for the location of a local extreme value. But you must determine whether they have an actual corresponding to max and mins, and we will discuss this later in section 4.3. Now, here's a couple graphs of the situation I was just talking about. Where could be a situation where I have a derivative equal to 0, but I do not have a local max or min? That is like one of our prime one is like an x cubed graph. Here is we have a little squiggle, and so right here at this point where it kind of changes direction, there is a horizontal tangent, but there's not a local max or min there. The other situation is if I have, it's kind of like a negative x cube root of x. Here, at this point where they change direction, here we have a vertical tangent where the derivative would not exist there, but it does have an f prime of c not existing, but we do not have a local max or min. So those two situations are what we're talking about up here, when it is possible to have a derivative equal to 0 or not existing and not having a max or min there. Okay? All right, very good. So here, we're going to just find the critical points. What are the possibilities of where a local max or min can occur? Okay, so basically we're asking the question, where is our derivative equal to 0 or where it does not exist? Now, this is a polynomial in this first example and the second example. So we know that a polynomial is going to be continuous and differentiable everywhere. So we're going to have a derivative at every spot. It's not going to be one of these situations where it does not exist. We're going to look at where our first derivative equals 0. So we want to take the first derivative. So remember, by the power rule, bring the 4 out front, but when I multiply that by 4, those 4's are going to cancel. You can think of that as a 1/4 x to the 4th. When I bring the 4 out front and multiply it by a 4th, I get a 1. Decrease that power gives me an x cubed. Same way here with this x cubed over 3. We get an x squared when I take the derivative minus 6x, and the derivative of 10 is 0. Here, I need to know where this is equal to 0 or not existent. Well, it's going to exist everywhere. So the only question is, where does it equal 0? So notice I would have something to be able to factor possibly. Maybe you have to use the quadratic formula. And so in this case, I'm going to factor first and bring an x out, which leaves me with an x squared minus x minus 6. And I'm going to keep going here by factoring this piece. Last sign is a minus, so we'd have a plus and a minus. Distribute my x squared. What do you multiply to get 6 that we subtract to get 1? And we want a negative 1. That has to be a minus 3 and a plus 2. So here is where I'm solving these equations, cubic, quadratic equations, whatever the case may be. And I have to yield out the roots of those equations. So I need to go down the line and say, what makes this 0 is 0. What makes this 0 is negative 2. What makes that 0 is positive 3. And these are my critical points for this function. Okay, moving right along to this next example. If you want to write that as 4/5 times x to the 5th, please do so if that helps you out with doing the power rule. If I take the derivative of this, I'm going to bring the 5 out front. Well, the 5's are going to cancel and leave me with a 4x to the 4th. Minus, this gives me a 9x squared when I do my power rule. I again want to find out when that is equal to 0. It is going to be differentiable everywhere. It's not going to have a d and e. So we just have to determine where this is equal to 0. Notice it is something I can factor, and this time the only thing that is common is an x squared. So I end up with a 4x squared minus 9. And that is a nice little difference of squares. So I get x squared. I'm going to go 2x minus 3 and a 2x plus 3. So it's very important for you to remember your factoring rules, okay? So here we go, down the line, what makes each one of those 0? This one is 0. This one, you can set it equal to 0, 2x minus 3 equals 0 and solve for x. But if you recall, the trick to these roots is take the opposite of what your eyes are looking at right here, which would be a positive 3 over this number out front, which is 3 over 2. Opposite of what you're looking at, which is negative 3 over 2. So I get 0, 3 halves, and negative 3 halves as our roots, which means that those are our critical points for this function. Those are the candidates at which your absolute max or absolute min will occur. Okay? All right, very good. Let's continue with another function. This one being a rational function. Notice here, I first want to kind of make note of what the domain is. In a rational function, we want to know where this is equal to 0. Well, if I square anything and add 1, it will never equal 0. So the domain of this function is all real numbers. So you want to make note of that in a rational function, because if a number is not in its domain, there's no way it can be a critical point or anything like that. So let's first find out where this is 0. Okay, actually, not where it's 0. Let's first find out the first derivative. Sorry. So I'm going to do a little ho-d-hi stuff on a quotient rule. Do ho-d-hi. So I do x squared plus 1 times x. Whoops, not times x. Times 1, because that's the derivative of x. Excuse me. Minus hi d ho, which would be a 2x, all over the denominator squared. So I'm going to clean that up a little bit on top. This gives me x squared plus 1 minus 2x squared. So that gives me a minus x squared plus 1 all over x squared plus 1 quantity squared. So here, again, is a situation where the denominator is always going to exist. It's not a DNE, so we wouldn't have to worry about that. But where is a fraction going to equal 0? Any fraction equals 0 when the top equals 0. So I need to extract out where f prime equals 0 is where the top equals 0. So where is negative x squared plus 1 equal to 0? Now, lots of different ways you can do this. You can divide by negative 1, factor that down, and find your two values. But I'm going to solve this using kind of the squared approach, solving that equation. I'm going to subtract over a negative 1, or excuse me, subtract over a 1, which gives me a negative 1 on the right side. I'm going to then divide by a negative 1 to get this x squared by itself and positive. So I get x squared equals 1. Then to undo a square, this is where I would square root both sides. So remember, this becomes then a plus or minus. Therefore, x equals plus or minus 1. Both of those numbers are in my domain. So those would be my possible, well, those are my critical points, which are the possible local max or local min of this function. Okay? All right, very good. And then let's do this guy. This one I just wanted to do just because of its derivative is a little bit more difficult, because you end up having a chain rule and you also end up having a product rule. So remind ourselves of this process. So taking the first derivative of here, we're going to take the first times the derivative of the second. So I rewrote it this way so I could take the derivative nicely. So I get x squared times the derivative of this. This has a composition of functions, so I have to do a chain rule on it. Bring the 1/2 out front, decrease that by 1, and take the derivative of the inside. Now the derivative of the inside here is not bad because it is just a 1, but if there was something other than that, you want to make sure that you do that chain rule piece on the inside. Plus the second times the derivative of the first, which would be a 2x. And so now here, this is a case where you want to make sure that you can factor very nicely here. I'm going to go ahead and take out a 1/2, and then that way I don't have a fraction on the inside. So I'm going to take out a 1/2. Each of them have an x, and each of them have this expression, x minus 1. So remember, when we have something in common, we have to take out the lowest power. In this sense, it'll be negative 1/2. So again, I'm going to take out a 1/2, an x, and an x minus 1 to the negative 1/2. And let's see what we have left over. So for 1, term. Here's my first term that I got to figure out what's left over. Here's my second term that I'm going to figure out what's left over. So make sure that you can eye those out. All right, so here's my 1/2. I took one of these, but I need 2, so I need an x in there. And I took all of this out front. So the only thing from this term that I need left over is that x, the one we can disregard. Now, for the second piece, 1/2 of what number equals 2? Well, 1/2 of 4 equals 2. I took out that x, but I need to figure out for this expression to have a positive 1/2. This is what's tricky, and most of the time it'll either be a whole number of some sort, but negative 1/2 plus what power gives me a positive 1/2? Negative 1/2 plus what equals a positive 1/2? Well, if I solve that equation by adding over a half, then x equals 1. So the power that's left behind, when I multiply this times this, I get this, is that power of 1. So it might be helpful for you to kind of practice some of those, because that is a little bit strange. All right, so I'm going to write this now as kind of rewritten. I'm going to take this guy to the bottom. I'm going to put the 2 in the bottom. I'm going to keep the x on top. So I have the x on top, the 2 on the bottom, and the x minus 1 to the 1/2 on bottom. But I'm also going to simplify this, and I'm going to do it pretty simply because this is a 4x minus 4 plus that 1x there gives me where I have a 5x minus 4. And that is my derivative. So here's the time when you want to make sure you can do those derivatives pretty efficiently. All right, so what's going to be our final answer for these critical points? Critical points, remember, is where our derivative equals 0, which would be the top, and where it is undefined. So in this case, it's a rational function. If anything in the denominator creates a 0, then that would be where our derivative is undefined. So for f prime equaling 0, I'm going to say, okay, 0 kicks out from here. And what kicks out from here? Well, the opposite of this over that. So 4 over 5 would be also another critical number. And where f prime does not exist is now where I turn to the denominator. And I look right here, if I throw 1 in there, then I'm going to end up having an undefined derivative. Therefore, it is a critical number. So 0, 4/5, and 1 are our critical numbers and possible local max and local mins of our functions. Okay? So I know this is a lot in section 1, but it is so crucial to know this section to move on to the next ones, okay? All right, so remember from earlier that if a function is continuous on a closed interval, then that interval must have an absolute max and min. That was the extreme value theorem. How in the world are we going to locate those, okay? So what we need to do here, here's some steps to answer the question, find the absolute max and min given a function. We looked at graphs and found absolute max and mins, but not necessarily functions. So, given it in a function form. So we're going to assume that the function f is continuous on a closed interval AB. Here are the process we're going to take in order to find absolute max and mins. We're going to locate the critical point C in our open interval AB, where f prime of C equals 0 or f prime of C does not exist. We just did that. Remember, those are candidates for absolute max and mins and local max and mins. Now, we are going to evaluate our function at every single critical point and at the endpoints of our closed interval. So we're going to have to include A and B. And then we're going to choose the largest and the smallest value of f from step 2 for the absolute max and min values, respectively. So basically, we're going to do exactly what we were just doing on finding our critical points, except for now we're going to go one step further and identify the absolute max and mins, okay? So let's do that for 3 of these functions. One of them being a trig function, another one being one that's not so nice either. So we'll account for that. All right. So the first thing that we have to do is to locate any critical points. So that means I need to first find the first derivative, which would be in this case 4x cubed minus 6x squared. And I need to determine what are those critical points. So in this case, it is a polynomial. It's going to be defined everywhere. The only thing I have to check is where this is equal to 0. Notice that we do have some common terms there. There's a common 2 and a common x squared, so I'm going to factor that out and figure out what I'm left with. And when I do a 2x squared times a 2, that gives me a 2x, that gives me a 4x cubed back. And if I took a 2 away in both of these, then that means I have a 3 left over. So again, try to distribute that back just in case to make sure that you've done it correctly. All right. So now we have to determine where those are equal to 0. These are our critical points. Okay, so the critical points, where is this equal to 0? Is it 0? Take the opposite of this over that, gives me 3/2. So the possible candidates for local max and local min, and in this case what we're looking at is absolute max and absolute min, is going to be at 0, 3/2. But we also have to include the interval that we're working on. Notice that 0 and 3/2 are within that interval, so I would have to check each one of those. So I need to know what is f of -2, what is f of +2, and what is f of each of my critical points. Now, this is where your scientific calculator, your graphing calculator could come in very nicely to help you figure out these values, because we have to take each one of these values and plug it into the original function to determine out what that value is. Now, I'm not going to take the time to do that on the screencast, so make sure that you can pause the screencast and also kind of double check to make sure that you can get these values as well. Either use your calculator or just by hand plug them in. So when I do f of -2, I get 32. When I do f of 2, I get 0. When we do f of 0, we get 0 also. And f of 3/2 is going to be -27/16. Okay? So once we have each one of those, now we can determine the absolute max and the absolute min by figuring out which is the biggest and which is the smallest. So here I have the biggest of the y values being at 32 and the smallest being at -27/16. So I can say that I have an absolute max of 32 at x equaling -2. So here's my 32 when x equals -2. I also then have an absolute min of -27/16 when x equals 3/2. So I wouldn't have had that just checking my endpoints. We had to have those critical points as well. Okay? Now, for the next one, what I'm going to recommend is that we do a little bit to our function first before we take our derivative. Now, this is one you can use a product rule with. And actually on my notes, that's what I used was the product rule, but it was really nasty. So in a case like this, remember, you can distribute that in. As long as that doesn't have a power of 2 or something like that, you can definitely distribute that in and get a new function and then be able to use the power rule. So I'm going to do this times that, which just gives me 2x to the 2/3 minus, when I do x to the 2/3 times x to the 1st, I have to add those exponents. Well, treat this as 3/3 added to 2/3 gives me x to the 5/3. And that actually will be a lot easier to take the derivative of than if you were to do the product rule. Okay, so now we just have to do the power rule twice. So g prime of x, if I bring my power out front, multiply it by 2 gives me 4/3. Decrease that power by 1 would be an x to the -1/3. Bring the power out front gives me 5/3. Decrease that power by 1, so subtract by 3/3, which would give me x to the 2/3. And this is my function that I have. Now, factoring these sometimes is a little bit more tedious than in other cases. Again, there's a common x for both of those. We want to take the smallest, which is a -1/3. I'm also going to pull out the third, the 1/3 in the bottom. So I'm going to pull out 1/3 x to the -1/3. And so when I take away that third in the bottom, I'm left with the 4, but I also took that x to the -1/3. So this is a 4 minus, take out the 3, I'm leaving the 5, but x to the -1/3 times x to what power equals x to the 2/3. Now I always like to try the power of 1 first. If I do a 1 there, when I times those two, I have to add those exponents. So -1/3 plus 3/3 does equal that 2/3. So these are my two factors that I have. Okay? Now, you can rewrite this if you want as 4 minus 5x all over 3x to the 1/3 to help you out by finding your critical points if you so choose, which might be helpful. This is a fraction, so we have to check where it's equal to 0 and where it does not exist. So in this case, where it's equal to 0, if you have to write that out, that's a little bit in a different order than what we've seen before, but if you write that out, 4 equals 5x, so x equals 4/5. So where f prime equals 0 is at 4/5, and where f prime does not exist is where the bottom is 0, which means that's at 0. Therefore, those are our two critical points. So once we have those critical points, now we get to evaluate our function at those critical points and at our endpoints. So what is g of -1? What is g of 2? That'll get our endpoints. What is g of 4/5? And what is g of 0? That'll get our critical points taken care of, okay? So, again, this is where you can plug this into your calculator and have it help you out, especially sometimes with those powers of 2/3. And so, in this case, g of -1, I will tell you, is 3. G of 2 is 0. G of 4/5 is going to be 1.03, so it is a decimal. So check that out, and g of 0, if I plug that in there, I get a 0. And so here, I need to evaluate what is the biggest and what is the smallest. Well, here is the biggest, and these two tie for the smallest. So there's two absolute mins in this case. So I have an absolute max of 3 at x equaling -1. And I have an absolute min of 0 at x equaling 2 and 0. So those are my two places at which we do have an absolute minimum. So again, making sure that you check all critical numbers and that you check any of the endpoints that you have for that. Okay? I'm just going to kind of divide off my little paper here. All right. So now let's turn to our last example to find some absolute max and mins. I did want to show you a trig function so that we remind ourselves of that on how to solve it. And then we have a word problem, and we will be then complete. Okay? All right, so taking this derivative, we have to remind ourselves what the derivative of sine is, but also notice I have a 2x here, so this is going to incorporate the chain rule a bit as well. So take the derivative of the full function, then the derivative of what's inside there. So f prime of x. The derivative of sine of 2x is going to be cosine of 2x, but when I multiply that by the derivative of 2x, that means I need to multiply by a 2, and I'm going to put that out front. Okay, now if you remind yourselves of the graph of cosine, cosine is one of those cyclic graphs in which it is going to be defined everywhere, so we don't have to worry about where it is non-existent. We have to worry about now where it's equal to 0. So when I solve this, notice that my angle is now 2x. Now, oops, I forgot about this piece. Hello. Let's do a little erasing. I forgot about the whole function there. Derivative of the square root of 3x. The square root of 3 times x, that is a linear, so I would just be left with minus square root of 3. That's now what I want to set equal to 0. Now, in order to solve for this, remember that this interval here is in terms of x. So x is a member of that. I now, in order to solve this equation, have to determine what the angles are in terms of 2x, because that's the angle that I have. Well, I'm going to multiply this by 2 and multiply that by 2. So 2x has to be between 0 and 2 pi. So let's get cosine by itself first. And I would do that by adding over the square root of 3 and dividing by 2. So I'm going to say that the cosine of 2x is equal to the square root of 3 over 2. That's the equation that I need to solve. So I have to remind myself, what kind of angle gives me the cosine to be the square root of 3 over 2? Well, if you remember your unit circle, or here I come with my 30, 60, 90 triangle, where it's 2, 1, and square root of 3. If I want the square root of 3 over 2 to be the cosine, that has to be the adjacent over the hypotenuse, and that is of this angle, which is a 30-degree angle. So the reference angle that I need is a pi over 6. But remember, for this angle, I need to go for all those cosines to be a positive root 3 over 2 from 0 to 2 pi, which is one time around our unit circle. So the angle 2x is going to equal, the first place it's going to be is at that 30-degree angle. But if you remember, all students take calculus or classes, however you remember that, cosine is going to be positive in the first quadrant, which is our pi over 6, and the fourth quadrant, which means that this is 12 pi over 6 is our 2 pi. So when I get around here, that reference angle of a 30-degree has to be 1 less than that. So I have to do 12 pi over 6 minus 1 pi over 6, which gives me 11 pi over 6. That's the other angle at which that's going to be equal to 0. I'm sorry, not equal to 0, equal to the square root of 3 over 2. So, to solve for x, now I have to divide by 2. But dividing by 2 with fractions is the same as multiplying by a half. So those go away. So I have to multiply each one of these by a half. So the critical points for this trig function is going to be pi over 12 and 11 pi over 12. Those are our two critical points. That those are the ones now that we have to match with, going back to the original a and b, 0 and pi, to determine our absolute max and min. So we're going to look at f of 0, f of pi over 12, and if I can squeeze it in there, 11 pi over 12. So these are our possibilities. And again, this is where I encourage you, make sure your calculator's in radians, but then go back, plug those into the, the original function is not just that, it is all of this. And I will let you know that when you plug in 0, you will get 0. When you plug in pi, you'll get a decimal of negative 5.441. When you plug in pi over 12, you will get 0.0466. And when you plug in the 11 pi over 12, you get negative 5.488. So again, I'm not going to spend time doing that in your calculator, but you can do that, and now we can assess what is the absolute max and what is the absolute min. Notice those are actually going to occur at our critical points this time. Here is the biggest, just barely over 0, and here is our smallest, just barely over that pi. So we have an absolute max of 0.0466 at pi over 12. And then we have an absolute min of negative 5.488 at 11 pi over 12. And those are our final answers for those. Okay. A little delay in the board. Sorry about that. But that's how you do those. And I know they are a little bit drawn out. You do have to know and master those derivatives a little bit to be successful at finding your critical points and then plugging in the endpoints as well to find out the absolute max and min. Okay? All right, our final example in this long first section of chapter 4 is that we have a projectile motion one in which we want to now find our maximum height. Okay? The maximum height. So that would be the absolute max or the absolute min. So we need to find our critical point, and then we also need to check at the end point. So if I plug in here, then I'm going to f prime of t is going to be, multiply out front gives me a negative 32t plus 64. That's my derivative. To find my critical point, I need to set that equal to 0, and I'm going to then subtract 64 and divide by negative 32 gives me a 2. And so that is my critical point of this function. Okay, so I need to, this is critical point, but notice I do have some endpoints here. So I need to look at what f of 0 is, what f of 2 is, and what f of 5 is. Okay, so I'm going to plug 0 into this function. Then I'm going to get 80. When I plug in 2 into my function, be patient with me, I didn't have this written down. I'm going to get 144. And when I plug in 5 to that equation, probably not going to happen at that endpoint, but I'll end up getting a 0. Oops. So what happens here on the interval from 0 to 5, now we get to choose the absolute max, which is at 144. And the question said, when does the stone reach its maximum height? That is at 144, but when is at 2 seconds. That is my final answer. So make sure that you answer the question. If it said, what is the maximum height? We would say 144 feet. But here it is, when does it occur? And that is at x equaling, or t equaling 2 seconds for that. Okay? All right, so that's the end of section 1. I know it was kind of long, but it is very, very important for us to get that in. Critical numbers are going to be very important to what we come into in section 4.3 when we start talking increasing and decreasing, and also concavity. So practice those. Make sure you know how to do those derivatives, and I will see you next time.